Hello, my name is Marc Heuse or Van Hauser. You might know me from the Hacker's Choice or THC.org, author of Hydra and THC-Scan and amap and well, some IPv6 stuff, which I kind of promised never to do again. But Dylan asked me, please submit something for conference. You know, Asia, they all need IPv6. So I said, okay, let's do some research, do something new, and that's basically the talk now. Yeah, maybe some first words about IPv6. I did a training here and talked to some people at the conference, and people kind of still seem to hope that we won't need that, or that IPv6 will not come, or it will not arrive within the next 5–10 years. So who cares? Not now, future maybe. Future generation will have to take care of that. That's not the case. North America ran out of IPv4 addresses, I think 3 weeks ago. So if you want IPv4 address in the US, you can't get them until you go to the black market. And everybody knows how much fun the black market is. So maybe there's a future deep web for IPv4 if you need to buy that, who knows. Future research may be upcoming. Yeah, but it's the situation. Even in Germany, we already have an ISP where you don't get an IPv4 address. Public one. You only get a private IPv4 address and an IPv6 address because they don't have enough IPv4 addresses for you. So this is a pressing problem. And that's why IPv6 is coming very hard right now. So, which is kind of a problem because it's still in a state where it's more like still in a kind of more developed play state. And people haven't really adapted to what it really means. So in this talk, I'll try to show you 2 areas which have not been much looked at. Yeah, let's have a look. I want to talk about 2 things. The first one is something which is so easy, so common if you think about it, but it seems that everybody misses it, and this is kind of the weird part. I call it the power of the /64. The second thing I want to talk about, and this is actually the main part of the talk because this is, let's say, the innovative part. It's how to bypass all the IDSs who try to perform IPv6. And you will see even that is not so hard. So, power of the /64, what do I mean by that? In IPv4, we get usually a Class C network. Wherever we are, we have usually a Class C network. In this Class C network, there can be a maximum of 254 possible machines, and that's basically it. So it's a small network, but large enough for this room to be everyone being in the same network and having an IPv4 address. In IPv6, we have a /64. Now, /64, of course, depends on how many bits you have. So is this big, is this small for a network? It's fucking big. It's 128 bits. So half of the whole network size is just for local addressing. I will show you the number in the next slide. So this is already big. However, as a customer, and I mean end user customer, DSL subscriber, who already gets IPv6, you don't get a /64, you get a /56. This is way more addresses and networks. And if you are on a 6-to-4 tunnel, for example, or you are a small-sized company, you get a /48. So what does that mean in numbers? This is the number of possible hosts in one network in a /64. You can put the whole internet as we have it today 4 billion times into one local subnet. So we can put the whole planet Earth with all the networks, plus the moon and Mars, all in one local subnet. I would like to see that switch, but that's basically the size that could be present in one local LAN. If we get to /56, we have even more addresses, and /48, I have no clue how to pronounce that number. That's what I call a fucking lot. So this is the number of addresses you have available just for yourself. And your neighbor, so next door neighbor in your house, has the same number of addresses available to him. So what can we do with that if you have so many addresses, something which we don't know in IPv4. In IPv4, we have scarcity of addresses. If you rent a server at a hoster, you get one IPv4 address and maybe a second one, and even many charge already for the second IPv4 address. If you go to a hoster and you want to have IPv6, you get a /56 and you don't pay anything. So you don't have scarcity, you have too much addresses. So what can we do with that? Basically, one person can be billions of persons. So what do we do with that? For example, we can use that to live scan networks. People think live scanning is not possible on IPv6. It's actually not true. It is possible and very feasible. It's just more time and effort than on IPv4. But what you have on IPv4, if you do a live scanning, it's very easy to detect. It's really easy to detect. If you do that on IPv6, and for every host on the other side you're checking if that's alive, you choose a different address on your network, that's very difficult to detect, because you never know, is this the same system? It's a different system. So it gets false positive, false negative. So just for scanning, using a different IP address for every target address is something very feasible and very easy. On the other hand, same for port scanning. Port scanning techniques and detection for port scanning is old stuff. Again, on IPv6, for every port you're scanning, you can use a different source address. And now all your port scanning detection techniques don't work anymore. Again, easy. Then, how would you do that? So I expanded the toolkit, the THC IPv6 tool, to be able to easily do that. So there was already an option where you could just say, please use this as a source address. Now I just added it with the option to do a /64 to automatically randomize the source address. Parasite is basically something like an ARP spoofer for IPv6. So whatever the return packets come, they automatically come to your system. And with these little commands, you can already do the live scanning and the port scanning in one tool, coming from every single packet from a random source address and bypass all the detection mechanisms. So this is the obvious stuff. I'll show you another obvious stuff, and this is, of course, denial of service. Lots of denial of service is already from random source addresses, so there's lots of filtering being in place, like reverse path forwarding on edge routers and techniques like that. But it is actually difficult if someone uses his regular real /64 of a compromised machine and uses all these billions addresses there. This makes things much, much, much harder. Actually, these options were already in there. So for SYN flooding or NDP exhaustion attacks, this is very easy. Then let's say you want to rig voting, internet voting, for whatever. This is a very simple shell script which just changes your IPv6 address to something random in your network, performs the voting, and then sets the next IPv6 address. Today, this is not even needed. I think it was last year when people on the legendary 4chan forum got together and rigged a voting on the Time magazine, where who is the most famous or most powerful person or something like that. And they rigged the voting in a way that the first letters of the candidates in the final votings pronounced a name of a RSC channel. In the beginning, they had some 500 systems with IPv4 addresses that were used to rig the voting, because from every IP address there was a time limit which said if you voted, you have to wait until these amounts of seconds until this IP address can vote again. Until this doesn't work for them on IPv6. They don't know IPv6, so there was no limit at all on IPv6. But even if they would had the same thing for IPv6, it doesn't help because you have so many possible addresses. So it doesn't help you. So this is the quick introduction on what you can do with large networks, because lots of people don't think about that. Protection is actually kind of difficult against that. So the easiest is if you want to block something, or if you would want to do an analysis on something, always do it on a full /64. So if you do port scanning, don't do it on IPv6, do it on the IPv6/64 analysis, because everything else is moot. And the products don't do that at the moment. So for all those who already have IPv6 and hope that their IDS or logging or whatever monitoring mechanism they have in place, that they will detect that, it's not working. If people come from company tunnels whatsoever, they have even more networks they can use. So for the port scan, you could expand this /64 to come from the /56. So you have more tries, more networks until you're blocked. And if you come from a /48, you have even more networks to come from until you're blocked. So, but still, it's something which is actually feasible for detection and blocking. If you try to do any kind of internet voting on stuff, tie it to an account, because this is really the only chance you have. So people have to register, have an account, and then put a flag on the account, okay, this account has voted and can't vote again. Okay, that was the easy stuff. In a discussion with a friend, when I talked about, yeah, you know, IPv6 addresses, blah, blah, a friend of mine, he came up with a different idea. He's not into IPv6, but when we talked, so he had this idea and said, oh, and I thought, oh, this is actually a very interesting and brilliant idea. He said, well, if you send to someone, to a server, for example, what if the server doesn't send the packets of the connection back to you, but to a different machine, or seemingly different machine? So basically splitting up connections. So you send with one source address to a machine, and the server sends to a different address the reply packets. This makes analysis of network connections really hard and lots of hands-on work. I wrote a little proof of concept tool for that, where you just use this /64 network, and then it chooses specific source and specific addresses, and you have the same on the server side. Actually, it runs in user space completely, so no need to patch the kernel and anything. And it was just, the coding time was less than 30 minutes actually to implement that, to split up connections that IDS doesn't know the connections anymore. So this is really so easy. You can even do more IDS bypassing, like small fragments and using random source addresses for the target network, and make it even more effective. But yeah, as a first proof of concept that it's really that easy, good enough. So the interesting part, IDS. Everybody loves IDS. Managers love IDS because they can show they did something to improve security. Auditors are happy because they can recommend something, because in their checklist says, yeah, IDS should be present. And the manager says, yeah, it's here, wonderful, shake hands, everybody's happy. Technicians don't really like IDS because it's lots of work, but they don't really help. The companies I know who effectively use IDS, they use it more for compliance management, like SNMP with public community string. Wherever this is used, this pops up, okay, and this has to be followed up. So it's more used for this, or the let's say, normal user who downloads nmap and performs a port scan or something like that. So something which is really, no security guy is happy to follow up these kinds of incidents, and because they're rather pointless. So, IDS. 1998, it was not the first paper, but it was the most comprehensive. It was the second and the most comprehensive paper on how to bypass IDS by Pacsec and Newsham. They showed how with playing with time-to-live values, with fake ACK, TCP ACK packets, etc., you get the IDS out of sync, and you can bypass basically back then all the IDS on the market. There's a British guy, Finnegan or something is his name. He followed this up in the last 3 years and still sometimes plays with that, and shows that even in current IPv4 IDSs, it's still possible against all IDSs to bypass them. So you might say, okay, how about IPv6? So if it works for IPv4 with an established protocol, which is an easy, not so complex protocol, it should be easier in IPv6. Actually, yes, so end of my talk. So I'll do a very, very quick IPv6 background because who knows about IPv6 here? Hands up. Yeah, that's very few. So very quick background so you see what the additional problem is in IPv6. So why is there more complexity and why do I go from hiding in complexity? So in IPv6, you have the IPv6 header, same like in IPv4, the IPv4 header, and then you have the TCP packet with the data. So this is how it commonly looks like. Instead of IPv4, it's IPv6. In the protocol field in the header, which is actually called next header in IPv6, is TCP, and then you have the application data. This is how 99.9% of the packets on the internet look like. Now, IPv6 is special as in that it has a fixed header. IPv4 does not have a fixed header, which is problems for routing and router vendor because it makes the routers more expensive because of more ASIC required, et cetera, et cetera. So in the standard, they decided to have a fixed IPv6 header, but you still need to have something like for options, for features that are not standard. For example, fragmentation is something which is optional in IPv6. So how do you do fragmentation if it's not part of the basic header anymore? That's where extension headers come into play. They are in between the IPv6 header and the TCP, UDP, ICMP, OSPF, PIM, whatever kind of upper layer you have in between. So you have the IPv6 header, which says that the next header is 0, which is the option, the protocol number for the hop-by-hop extension header, which shows in its next header option field that the next thing is a TCP header, and that's basically it. If you have two extension headers, it looks like that. First, the IPv6 header, which shows the next header is 60, which would be destination header. Next header is 44, which says it's a fragmentation header, and this specifies the next header is UDP. This is called extension header chaining, because you can chain extension headers. How many extension headers do you think you can have in an IPv6 packet? With this kind of audience, it's a difficult thing to get an answer for that. I understand that. Who think that you can have less than 10 extension headers in maximum in such a header chain? Hands up. 255, interesting idea. Who thinks it's less than 255? Hands up. Yeah, let's say it's 1,500, the standard MTU on all Ethernet. Who thinks it's more than 255? Yeah, 4 people, and you are right. It can be up to over 8,000 extension headers. 8,000 of these thingies in between and until you finally get to something TCP, UDP, or whatsoever. You will see that there can be some kind of complexity so far. Yeah, this is how an extension header usually looks like. The first byte is what is the next header, and the second is the length field for this is the size of this extension header. This is how all the extension headers look like. So I won't go into detail on all the kind of extension headers. The important one, which is interesting, is the fragmentation header, because fragmentation is optional. Why is it optional? Because less than 1% of the packets on the IPv4 internet are fragmented. So it's something which is a rare occasion. So why should this feature be in the header? It just takes up unnecessary space. So it's an option, because in IPv6, fragmentation is even more rare than in IPv4. Don't go into details why, but depends on how it is done on the network, so when fragmentation actually occurs. So in the fragmentation header, it's always 8 bytes in length. The next header always points to what is the next header, like TCP, UDP, ICMP, or another extension header, of course. You have the fragmentation offset, which is, as everything in IPv6, it's counted in octets, so in 8ths of bytes. So if it is 0, it's the first fragment. If it's something like 100, so it's at the offset of 800 bytes, it's of course not the first packet. And you have a flag, the more fragments bit. If this one is set, it means more fragments are coming. If this bit is not set, it means it's the last fragment. So in IPv6, we have standard fragmentation with one special feature. The special feature is something that's not possible with IPv4. It can be the first fragment, fragmentation offset 0, and it can be the last fragment as well, more fragment bits set to 0. So first fragment and last fragment in one fragment, yeah, it's basically a dump header. But it's possible in IPv6, and actually for some weird things, it's actually needed. So it's actually a feature. So we have fragmentation, and we have lots of extension headers. Like we could have over 8,000 extension headers. So the first view in this is, wow, this is big, this is a lot of stuff. What can we do with that? So when we talk about, OK, this as a base as additional possibilities that we have to bypass IDS in comparison to IPv4 stuff, the question is, what is the basic methodology to actually find IDS bypasses? The first step might surprise you, because first is, what packets are actually accepted by the target OS? There are lots of IDS bypasses you will find, but actually Windows or Linux will just throw the packet away. And then you find a great bypass that just doesn't help you. Yeah? So actually the first step is rather check what is kind of quirky in packets you can generate that, for example, Linux, Windows, OS X still accept. With these, you create test cases. OK, with these quirks, if I do the packet stream like that, is this being picked up by the IDS or not? That's the test cases you create. And then you should have a farm of different IDSs and try the exploits. And that's basically what I did. And yeah. So the attacks on IDS I classify in two different kinds. The first I call the disruptor packets. Disruptor packets means the IDS sees there is a connection, loses the state on the connection, so it can't do any interpretation on the content anymore, but it sees something is kind of wrong, but doesn't know what. So it can give a whatever standard common alarm, but it can't tell you it's this attack or that attack, or it's really critical, or it's already, oh, your network's already owned. It can only say, oh, this is kind of weird, help me, help me, help me. An example, a really appellant example, is Snort in that regard. So Snort is, for IPv6, is really something I cannot recommend. For example, for this, if you want to do disruptor attack against Snort, and this is documented and known, so this is nothing like, oh, 0 day or something. So this is long known. Basically, you just put over 8 extension headers in your packet before you do your whatever kind of attack. And Snort will simply say, yeah, you know, there was a packet with too many extension headers, but no clue further than that. Help. Yeah? So whatever SMB, SQL injection, whatever kind of exploits you want to do, just prepend that in your packets with lots of extension headers, and Snort will just cry. And yeah, is it critical or not? Well, all depends on human interaction. OK, where's the PCAP for this alert? Fuck, lots of extension headers. So what does this actually do? OK. Yeah, but it's not automated, block, etc. As I said, it's documented. It's actually a configuration option in Snort. They have an option which is called config max IP6 extensions, and set it to 8. If you want more security, you can increase the number to 200, 500, but it doesn't make sense. A real IDS product or tool should walk through all the extension headers. It doesn't matter how many. It's the typical, yeah, you know, performance, it's more important than security in a security product. Like if you have a firewall, the most critical selling feature is the throughput. Yeah, same kind of mislogic is kind of here. Yeah, so this, even to have that, is a bad idea. So this is just one simple example for disrupting the IDS. The other attack is, I call the ninja packets. Why a ninja? Because basically the IDS is completely blind. It doesn't see anything in the first place. So it can't even say, oh, there is something fishy, or there is an attack. No, it doesn't see anything. So these are, of course, the golden goal you want to go for. This would be perfect if you would find any kind of these. So I will show you several examples, of course, of this one, because these are the most juicy ones. So for this test step one, what packet weirdness is accepted? In my toolkit, I have various tools for that. The best, actually, for this is the so-called Firewall 6 tool, which contains, forgot, something like 25 test cases on how you might be able to bypass ACLs, firewall filters, extension headers, fragments, overlapping fragments, invalid length in fields that are aligned in a way that they can make misinterpretation on the packets, and lots of weirdness stuff. Fragmentation, which show a different protocol depending on if it's the first, second, or third fragment on what is the next protocol. I might go back to that and show you this on, because I forgot to tell you that one. Here, every fragmentation, every fragmented packet in one fragmentation stream has the same fragmentation ID. Yeah? So let's say it would be bad for security, but let's say it's just counted upwards. So the first fragmentation ID would be 1, and for that packet that's been fragmented, all the fragments would have the fragmentation ID of 1. That's how they can be aligned together. It has a next header field. Let's say it's a TCP packet, and you have three fragments. What if the first 2 fragments show it's a TCP, but the third fragment shows it's UDP? What will the end system, the receiving system, do with the packet? Will it interpret it as UDP or TCP or throw it away? And what will the IDS think? And what will the firewall think what it is? Is it TCP, UDP? The IDS can't throw it away, so they have to decide is it TCP or UDP. Yeah? So this is for one of the many attack examples you can do. Yeah. So my main targets are Windows and Linux. Linux and OS X are very, very close to the implementation, so there's very little difference. So actually, all the results for Linux are also working for OS X. I try to put it in an easy picture because pictures are easier to understand. Linux is very selective on what packets they accept. So it's like, yeah, it must be like this and like this. If it's not like that, no, then I don't want the packet. And Windows is more like, more, give me the packets, I eat them up. So that's Windows. Yeah, they don't care how weird the packet is. Yeah, I'll eat everything. Yeah, whatever. And you know, the fat Americans, that's basically. And this is the slim Asian. Yeah, or yeah, I'm joking. I know how much Asians eat. Sorry, guys, I saw you. Yeah. But that's how you can imagine it. Maybe relate. So for Linux, they allow an unlimited number of destination headers. So 1,000 destination fragmentation header, yeah, give me, fine with it. Yeah, accept any packets. They only allow 1 of each of the other extension header types. That's actually good. So this is not so good. This is good. They only allow only 1 fragmentation header. You might think, yeah, why shouldn't I accept more than 1 fragmentation header? Well, we'll get to Windows in a moment. Yeah, extension headers are not allowed to be fragmented. There is a draft by Fernando Gont, which is on oversized extension headers, which is not an RFC yet, but Linux has it already implemented. So Linux drops anything where the extension header is so large that it breaks the packets into fragments. And if you have the fragmentation stream and the next header in one of the packet is different, it won't reassemble. Because for Linux, they take the fragmentation ID plus the protocol ID to say this is to identify each fragmentation stream. So this is actually a really good approach. So for Linux, the only thing where I say they should change this is unlimited destination headers. They should set this actually to only allow 2 destination headers, because this is actually what the RFC recommends. But otherwise, this is actually pretty good already. Yeah, and overlapping fragments are not allowed. So for Windows 7, how does this look like? Yeah, extension headers, whatever, give me. You can also have unlimited fragmentation headers. What does that mean? Yeah, you can have multi-level fragmentation. You have a fragmentation stream, let's call it A, which carries other fragments that when they are reassembled, get to a different fragmented chain, which then it's again and again and again. Like these Matoshka things, which one is in the other. That's something you can actually do, and Windows will just happily do it all. Yeah, they don't care. Extension headers are allowed to be fragmented in multiple fragments, any size, they don't care. However, now this has changed, because that was one of the problems they had in the implementation. If you change the next header type in the fragment change, now they won't allow it anymore. And they don't allow overlapping fragments. This is actually something from, I think, 2011. There was an RFC from Cisco which disallows overlap. Before, Windows and Linux were allowing overlapping fragments. Really bad idea. And you have a different attack type, which is not really overlapping, but resending a fragment. So you have a fragmentation stream, and you can resend packets from the fragmentation stream with different content. So it must be at the same offset, must be the same length, but it can be with different content. And the last one that is received is being used. And this already tells you, wow, IDS bypass made easy, right? This is the NSA option for let's not be seen, baby, basically. Yeah. Actually, I didn't need to implement that, but yeah, let's see that. Test step 2 and 3, create test IDS bypass based on the packet weirdness, and let's see what gets through. My test bench was on Suricata, on Tipping Point, and on Snort. SourceFire was also on the list, but I was working together with ER&W, who thankfully helped me in using their infrastructure to test that. We couldn't get it running, so the update process was kind of broken. So didn't work in 2 days to get that running. So SourceFire is not included, but basically use the same engine, so should be the same result. So all were configured to the highest setting. For Tipping Point, that's the hyper-aggressive mode. That's the one where they recommend, yeah, you should basically not do that. You will have so many false positives, don't do that. It's the highest aggressive mode. For Snort and Suricata, really every single rule was enabled, which was actually for Snort a problem, because the CPU load got so high that for a detection to be made, it took 45 minutes because of the higher load. So it was kind of even in denial of service attack on Snort. Yeah. And of course, at the time of testing, it was the newest rule update there was of the rules and the engine. Okay. And this is basically the main slide of the presentation. I put it in one slide because that's easier. These are the various kinds of tests, and then you will see what are the test case results on the 3 IDS. First, you might be interested, actually, what kind of test did you do? I decided to make it the easiest possible for the IDS to detect something. For example, you could do an SMB attack or Samba attack, which is multi-step, etc. And as an attacker, it's easier to disrupt the IDS on the connection so that they get out of sync with the real connection. So what I did was basically a simple GET request where all the TCP data is in one packet, so they only have to look at that one packet, and that had an SQL injection exploit in it. Like really like one parameter, 1 equals 1, etc. The standard. And that's why, of course, they all detect that. Yeah? But that was the basic test case. Not to use a difficult exploit that's harder to detect, but an exploit that's standard and the easiest possible for the ACE to detect. Yeah. So the basic task to have one fragmentation extension header in there. not surprisingly, of course, they should detect it. Come on. Otherwise, you should sue your vendor because he's selling you a malfunctioning product. But it already gets interesting if you send 2 fragmentation headers. You already have a ninja attack against the tipping point. 2 fragmentation header and tipping point doesn't see any attack. It doesn't report anything. Like, this is really like, what the fuck? The funny thing is, when you send 9 or more fragmentation headers, Suricata still detects. Snort shows this error message I showed you, like, oh, too many extension headers, help me, help me. And tipping point will also show, oh, there are lots of extension headers in this one. Yeah, so actually, tipping point gets a little bit better now that there are more extension headers. Yeah, which also, well, okay. But this is clearly a bug. Or, as I call it, interesting attack vector. Then a large destination extension header that fragments the packet into 2 parts, where the TCP payload is in the second fragment. Suricata and Snort detect this kind of really standard attack, and tipping point again just says something, oh, you know, this is extension headers, this is kind of weird. Yeah, no. Yeah, but doesn't tell you that your system was just owned. Yeah, and to see some generic IPv6 reassemble weirdness, a message doesn't tell you, okay, I'm owned. Yeah, so this is problematic. And this is really not like, oh, super rocket science to figure that out. I mean, these 2 can do that. Mini fragments. Mini fragments is you take the big packet and fragment it to 8-byte packets. So you have many packets that are very, very, very small. Again, how hard can it be to just collect the fragments, put it back together, done? This is not with any evasion or out of order sending or anything. Yeah, this is just basic. Yeah, just chopped in little pieces and send them on the path. You know, like a salami, like Italian salami, which you chop very fine. I'm a vegetarian, but I know how thin they are chopped. So, yeah. Again, tipping point. Whoa, you know, this is so weird. No, it's not weird, but yeah, this product sucks. Then the most difficult attack for an IDS is if you can send packets that are received by the IDS, but they don't reach the destination. And this is something which is actually very common. So you have a central place where you have the IDS, and the server network, the MSET networks, whatever, is behind that. So it is 1, 2, 3 hop counts away. So what you do, you send the packets with a hop count that the IDS still sees the packet to the destination, but the hop count is not large enough to actually reach the destination. Well, you might think, well, if there is a fishy packet coming with a very low hop count, they would say, whoa, this is kind of unusual. I mean, by default, in every network on IPv6, you usually have a hop count of 64, which is more than enough. So you will never see basically a hop count below 10. Doesn't happen. I have never seen that. Haven't seen it ever on IPv4. Yeah? So this is easy to detect, but yeah, I can already tell you none of this is happening. So this is a well-known easy attack on IDS. So this is something IDS has to protect against. So in the first attack on the, let's say the hop count is different for some packets so they don't reach the target. What I did was basically I took the same TCP packet, filled it with random garbage. Basically it was just an X, but let's say it's random. Recalculated the CRC checksum and sent it on the way with a hop count so they don't reach the target. Yeah, as you see, so Suricata and tipping point are both saying, you know, there are packets which don't really match in the connection. And that's it. Where Snort, surprisingly, can still detect, oh, there's the attack here. OK, let's try something else. I mean, this is OK, but yeah, we rather want something like this, right? I mean, this is the holy grail. So how about if we don't send TCP data, but we send a reset of the connection? Yeah, now we're getting somewhere. Surprisingly, this is where a tipping point shines. Sending fake RST packets, they don't seem to care. They seem to ignore RST packets, actually. Whereas Suricata says, oh, it's a connection reset, wonderful. I can take this out of my list of connections I have to follow. So totally bypass Suricata and Snort completely, flying blind through all your attacks. Next one, sorry, I already passed and got the prize. Of course, we need something for tipping point too, come on. So you fragment the data, basically the same attack like here, but you fragment the data in small pieces, duplicate them so the real one reaches the target and the other one don't reach the target, and the ones who don't reach the target, you put again with random data or X. Yeah, if you do that, tipping point doesn't see any of the attacks anymore. And yeah, to have fake 9+ fragmented TCP data, so it's kind of this attack combined with this attack with a hop count which doesn't reach the target. Only Suricata says this is not good. And actually, the weird thing is that it reports invalid TCP checksum. That's the error Suricata reports, invalid TCP checksum. This should be the clear indicator that you're currently owned, right? Invalid TCP checksum, high critical risk. Okay, for the not TCP people, no, this is basically like, okay, packet weirdness on the network. This is what Suricata tells you, and on Snort and tipping point, you're going through blind. So, still we have the question, Linux, Windows, who would eat which kind of packet? So I put it here, and you see the, oh, okay, thank you, Windows, thank you, Microsoft. Yeah, they will tell you to do this for compatibility reasons, because nowhere on the internet these kind of packets are being sent, but there might be, so yeah. So the Windows is the big problem. With Linux, yeah, these work, but you see they all picking it up, so this is not, you don't have an attack there. The only attack that helps against Linux and also OS X is if you use mini fragments and you have the tipping point, or with the hop count not reaching the target attack types. That's the only chance you have if your target is Linux or OS X. If it's Windows, you have lots of options. Yeah, so basically how you would do that as an evil attacker, you would check what is my target, for example, Linux or Windows. You would check out, okay, what IDS is present on the network. If you can't find it out, because sometimes you can just by checking the DNS entries, if you see a host named Snort or Suricata, a tipping point, okay, it's easy. Or you see a host name with IDS management, and then you just check the ports and you see which product it is. Or even if this fails, you can do various kinds of IDS stuff and see, so IDS evasion stuff, and see which one they pick up and which they check on the host. Okay, there's some attack from there, so. And if they log into the machine, okay, they detected that one and can. So there's still many ways, even if you can't find the IDSs on the network, which is highly unusual. And then you basically have your matrix and say, okay, this is my target, I have this IDS, so this is the attack I use to do my real attacks on the network not being found. Yeah. So, as we can see here, tipping point, really bad product on IPv6. I don't know, no clue how good they are on IPv4, but on IPv6, they're kind of scamming the customer. Suricata once had the same engine as Snort, but at some point they were not happy with that and wrote their own engine. And if we compare Suricatas to Snort, they are better. So clear recommendation, if you have an IPv6 network is, and you have to use IDS because every IDS can be bypassed, Suricata would be the obvious choice here. So there is, of course, also a tool for that. It's called Fragrouter 6 because there is a very famous IDS bypassing tool for IPv4, which is called Fragrouter. Yeah, so this tool is, of course, called Fragrouter 6. Very easy implementation. I use Linux IP6 tables and FQs, so I can do everything in user space. I don't have to patch a kernel. It's still work in progress, so it has lots of, all the IDS evasion stuff I showed you here is in there, but there's still some more I want to do. But the best thing about this kind of implementation is that you can use all your IPv6 tools. Nmap port scan, no problem. Some raw packet IPv6 stuff, Scapy you want to use, no problem. you can use all your IPv6 attack tools transparently with that, either from your own machine where this tool is running, or as an intermediate router if you have, for example, Nessus on Windows, but you want to use it with these IDS evasions. So you have the Windows machine, you have the Linux machine, which transforms the traffic and sends it to the target network. So this makes it super flexible. Yeah. It can send any number of fragmentation destination headers, fragment packets to any size, fragment to over large destinations headers, and has the hop count -1 attacks. As I said, still work in progress, so there's still some other stuff I want to try out. But the problem is I don't live near the ER&W guys, so I don't have this test bench to me available on so easily. So it makes it a little bit hard for me to do further experimentation on that. Yeah, but it was lots of fun. So how can you actually protect against that? Two answers to that one. The first one is easy for you to implement, actually, and that is to filter on your internal network anything which has exception headers. You could even internally say even everything that is fragmented you can filter, because internally you should not have any kind of tunnels, and tunnels are the only occasion basically in an internal network where fragmentation happens. So if you don't have any tunnel, IP624, 426, whatever kind of tunnels in your network, you should not have any kind of fragmentation. So internally you could say any packets with extension headers, drop. For example, as standard ACL on routers. And then most of the attacks, would not work anymore. Yeah. The other thing you can do, or what we could do as a community, to write a new RFC to make things better. For example, the current RFC on IPv6 specifies, well, you should order the extension headers like this. So this extension header should be before that one, should be before that one, should be before that one. But it is like should. And it should rather be changed to must. Because if this is changed to must, it's much easier to parse. Also, to limit in the RFC the number of occurrences of each extension header, how often are they allowed, which is basically only once for each extension header, and only the destination header being allowed to be presented 2 times. If you do that, automatically the number of possible extension headers is reduced to 9, I think 9 or 10 for the current number of extension headers, and even that you will never see on the network. There is a good start. This is the draft from Fernando Gond. Implications of oversized IPv6 header chains, which hopefully become an RFC. OS X and Linux already has that implemented mostly, but it's not complete yet. So it would need another draft for getting this right. Yeah, that's basically it, but I have one more thing. That was 2007. 2007? I think it was 2007, when I first showed the Nalo service on every single OS platform by flooding a local network with router advertisements. So this has nothing to do with IDS bypass. It's just looking back at history. So you flood the local network with random router advertisement packets, which trigger, if you don't know that, update in your routing table, and if you do auto-configuration in the packets, also that the systems configure themselves a new IPv6 address. If you do that with 1 million random packets, it means 1 million routing entries and 1 million new IPv6 addresses. What could go wrong? Yeah, of course, all the systems crashed or 100% CPU load, etc. There were some fixes. Microsoft was actually the hardest one of all to actually fix that, or even, well, they didn't want to fix that, so it took them 2 years to fix that. 2 years. So they kind of fixed that. So I did actually a training during the IDS assessment when I was in ERW. And yeah, guess what happened with current operating systems? OS X Yosemite, crash report. Windows 10, oops, we've got a problem. And Ubuntu, but that was because of a buggy version of the network manager, just shut down. So power cluck off. Not regular shutdown, but really power off, cluck, gone. Yeah? Just with using that 7-year-old tool. Yeah. Here in the training, we couldn't reproduce that, but nobody had Windows 10, and Windows 7 and 8 are not affected actually by that. And the OS X machines were sadly also not affected here in this training, so I don't know what the special occasion was, but it was great. You have a training, and half of the laptops basically all go, and you just wanted to show an old bug. Yeah. So part of the THC IPv6 packet, of course, which I will put online in just after the talk and before lunch, so you can already download and play with that stuff. And now we have time for questions.
Hey, thanks, Mark. It was a great presentation. I have a question. You talked a lot about the network layer and the implications of IPv6. I would like to ask about something you touched at the beginning, and it was more about the actual application layer and how this changes things and protections we have currently. I was wondering, do you think that this will lead to a situation where more and more stuff on the internet or accessing resources on the internet will be actually authenticated and will require to identify you and know your identity, not only, let's say, your IP address, which doesn't say much about you with so many IP addresses?
I don't think so, because this is more like you run an attack, and the problem is that your attack is detected and then your IP is blocked, for example. Or you try to vote on, let's say, Next Germany Superstar or The Voice or whatever crap TV show there is, and you select, yeah, this should be the winner, and yeah, your IP is accounted for. So this is nothing like access to protected content. But this is where you can actually misuse the big address space you have available, something you don't have in IPv4. So on IPv4, port scan detection, okay, this guy is port scanning, automatically lock them down, for example. And on IPv6, it can't work like that. But so that more access to something will authenticate it only for the voting part, but that's basically it. And even the voting part, you can implement it like you vote for /64, and even if a user is technically able, he has because all the DSL users, they don't know they have a /56, but they have. So if they know that, they can do some command line magic foo and use the other networks. And then you have 255 votes instead of just one. Still, if thousands and thousands of people are voting, this is statistically not that significant. So the thing is, people must get aware of that and do the proper protections.
Thanks.
Any more questions?
I think this stuff was easy enough, right?
Okay. Thank you, Van Housen, for your talk.